My name is James Oxford. I'm personal assistant of Jose Luis Luna Sanchez, and I'm going to present this poster called Nitrogen-Doped Carbon Quantum Dots from Banana Peel, Synthesis, Characterization, and Potentialities. This research has been developed at UPIDO IPN at the Photothermal Techniques Laboratory. Abstract. Carbon quantum dots have gained great importance due to their optical and physical properties and the wide variety of methods and materials used for their synthesis. In this work, we compare two synthesis methods: traditional hydrothermal and microwave-assisted hydrothermal. Banana peel flour was used as a source of biochar, and urea was used to dope the carbon quantum dots with nitrogen. The ultraviolet visible absorption spectra of the synthesized carbon quantum dots are very similar for the two series of experiments, presenting an absorption band at 254 nanometers. The particle size measured by transmission electron microscopy was 9.9 nanometers in both cases. However, the Fourier transform infrared spectra shows clear differences. In the infrared spectra of the samples processed by the microwave-assisted hydrothermal method, more chemical groups found on the surface of the carbon quantum dots are identified. Introduction. The research of Manji Bawendi, Louis Brous, and Alexei Ekimov were awarded the Nobel Prize in Chemistry in 2023. They synthesized quantum dots from semiconductor materials. Based on their work, many studies have been conducted varying the synthesis method as well as the materials. Carbon quantum dots are similar to quantum dots from semiconductor materials. They emit light when illuminated with ultraviolet radiation. However, they have the advantage of not being toxic. They can be obtained from any material containing carbon, minerals, and biomass. Therefore, several synthesis methods have been developed that vary the carbon source, the synthesis reactor, and the energy dosage, and are carried out in ambient and inert atmospheres. Thus, comparative studies are necessary to identify potential advantages and disadvantages, as well as to allow us to propose the physicochemical route followed by the synthesis. Here, the traditional hydrothermal and microwave-assisted hydrothermal methods are compared. Synthesis. This image schematizes the objective of the research. We start with banana peel flour and its conditioning for the synthesis. Then, the synthesis of the carbon quantum dots is performed, which in our case is doped with nitrogen. On the left, the hydrothermal method, HT, on the right, the microwave-assisted hydrothermal method, MWHT. The resulting carbon quantum dots will be functionalized with molecules that will act as anchors to attach the carbon quantum dots to tumor cells. The indicated molecules are different because the expected chemical functional groups on the surface of the carbon quantum dots are different and have different reactivity due to the synthesis route. After functionalization, their activity on living tumor cells will be evaluated. The results will indicate their safe use in the human body. Two synthesis methods were chosen: a traditional hydrothermal method and a microwave-assisted hydrothermal method. In both cases, 0.4 g of carbonized banana flour, 0.6 g of water, and 1 to 9 milligrams of urea were used. In the hydrothermal process, the reactant mixture was heated to 3000 degrees Celsius for 1 hour with a 15-minute preheating phase. After 1 hour of reaction time, the reactor was allowed to cool to room temperature. The calculated pressure in a 50 milliliter sealed reactor was 1.8 megapascals. In the microwave-assisted hydrothermal process, safe operation, as indicated by the Mars 6 equipment operating limits, was achieved by a 15-minute preheating ramp to 80 degrees Celsius, with the pressure limit set at 600 kilopascals. Within these operating limits, the synthesis reached a temperature of 78 plus or minus 2 degrees Celsius and 23 plus or minus 2 kilopascals. In the images, we can see the banana peel flour before undergoing the carbonization process. On the right, the carbonized banana peel flour is seen. This process is a pretreatment. In the middle left, the hydrothermal reactor used is seen. It is a Teflon container hermetically sealed inside a stainless steel container. Below, the hydrothermal container inside the laboratory furnace. It should be noted that this reactor does not have holes for filling it with inert gas, so it was decided to use ambient atmosphere in both systems. On the right side, the reactor used in the Mars 6 equipment is a Teflon container with a fiberglass reinforcement. The lid has holes for the fiber optic temperature sensor and another hole for sensing pressure. The reactor is placed in a cartridge that holds it in position on the rotating platform. In the center, the product, the carbon quantum dots, can be seen. When illuminated with ultraviolet light, they emit wavelengths very close to each other. This will be verified later with photoluminescence spectroscopy. This graph shows the ultraviolet spectrum of untreated, oxidized, and carbonized banana peel flour. For oxidation, the banana flour was heated to 300 degrees Celsius for 1 hour. For carbonization, the banana flour was heated to 300 degrees Celsius for 3 hours. The spectra show that the absorption band of the banana peel flour narrows. To eliminate the possible influence of the initial functional groups, carbonized banana peel flour was used. This would provide a larger surface area for the carbon quantum dots to add the functional groups of interest. These are the absorption spectra of both synthesis series. An absorption band is observed at 242 nanometers. This band is linked to the excited pi-to-pi transition of carbon bonds. No band is observed linked to the excited into-pi transition, which is linked to the transition of other orbitals to the excited pi orbital. The TEM images show particles with an average size of 9.94 plus 0.89 nanometers. Their shape is irregular. These are the Fourier transform infrared spectroscopy spectra. The functional group peaks are observed in greater abundance and more clearly in the spectrum of the samples processed using the microwave-assisted hydrothermal method. It is expected that there will be more sites for functionalizing the quantum dots in these samples. The carbon quantum dots produce present notable differences that are clearly observed when comparing the Fourier transform infrared spectroscopy spectra. There are a greater number of functional groups on the surface of these quantum dots, and these will be used to functionalize their surfaces. No differences were found in the particle size distribution. The absorption spectrum showed an absorption band in the 290 to 296 nanometer range. We would like to thank CICITI, COPA, and CGPIP in Mexico for their partial funding. We would like to thank the Center for Instrumentation and Microscopy at ENCB, the Matea Group at UPIDA, and the Department of Physics at Sinvestab for their support in sample characterization. These are 3 of the references used in this research.